The next section we'll investigate deals with enthalpy, which is abbreviated delta H. And there are 6 main things that we can use when we talk about relationships involving delta H. We can calculate the delta H of a reaction. With each of these chemical reactions, there's going to be reaction stoichiometry. So we can look at stoichiometry to determine the amounts of products and reactants and how much heat they're going to give off or absorb. We can use something called Hess's law. We can look at something called calorimetry. We can look at bond enthalpies and then talk about standard enthalpies of formation. So let's go over a few relationships involving delta H. The first one we will look at and that we need to recognize is that delta H is an extensive property. And what we mean by extensive property is that it's going to depend on the amount. So the amount of energy we can get from a particular chemical reaction, let's just say to power your automobile using gasoline, it's going to depend on the amount. The amount of work that we can get depends on how much gasoline you have. So if you have a full tank of gas versus a half a tank of gas versus a quarter tank of gas, you're going to be able to travel different distances with that amount of gasoline because the energy, or the delta H, depends on how much we have. We can represent this in a chemical reaction by saying if we have N2, which is a gas, plus O2 gas, giving us 2NO gas, the delta H here for this particular reaction is going to be 180.5 kilojoules. Okay? If, on the other hand, we have a half of an N2 in the gaseous state plus a half O2 also in the gaseous state, giving us 1 mole of NO gas, our delta H for this particular reaction is going to be 90.25 kilojoules. And notice that when we produce 2 moles of this product, we're going to get, versus 1 mole of the product, we're going to get half of the amount of energy, because delta H is an extensive property that depends on the amount. We can also use the principles that we talked about when we discussed limiting reactants. And in this case, this energy is going to be involved in the reaction stoichiometry. So we can say that when 1 mole of N2 gas reacts with 1 mole of O2 gas to produce 2 moles of NO, we're going to get 180.5 kilojoules of energy. And we can use this as a conversion factor. So for example, if we reacted 42.0 grams of N2 with excess O2, we can use our conversion factors to determine how much we have here, because we know that 1 mole of N2 gas is going to correspond to 180.5 kilojoules of energy. So first we need to convert this over to moles. So we use the periodic table to say that 1 mole of N2 is equal to 28.0 grams. And we also know that 1 mole of N2 is equal to 180.5 kilojoules of energy. So if we react 42 grams of nitrogen with excess oxygen, we're going to get 42 divided by 28 times 180.5, or 271 kilojoules of energy. And we can use this delta H value just like we would use a conversion factor. The second thing we need to recognize with a relationship involving delta H is that the delta H changes sign when the reaction is reversed. So when we look at a particular reaction, such as 2NO as a gas becoming N2 gas plus O2 gas, our delta H is going to equal negative 180.5 kilojoules, which is the exact opposite as what we saw up here in this particular reaction. So when you change, or when you reverse a reaction, the delta H is going to change sign. Another thing that we have to be particularly careful with is the phases of our reactants and the products. Because the third thing that we have to keep in mind is that the delta H depends on the physical state of the reactants and products. So for example, if we had 2 moles of water in the liquid form going to 2 moles of water in the gaseous form, our delta H is going to equal positive 88 kilojoules. So anytime we are expressing a thermochemical reaction, we have to make sure that we indicate the phases of all our reactants and all of our products. The fourth thing that we're going to look at, which is a very, very important relationship, is something called Hess's law. And Hess's law is based upon the fact that delta H is something called a state function. So what we can say about this is that when a system undergoes a change from state 1 to state 2, delta H depends only on the nature of states 1 and 2 and not on any details of the path. Another way we can reword this is to say that a state function is independent of path. Some examples of state functions are delta E, delta H, delta P, and delta V. Some quantities that are not state functions are going to be distance, heat, and work. So we can use Hess's law anytime we have a state function. And in the next video, what we'll discuss are some example problems of how we would use Hess's law to calculate delta H, or the enthalpy of a particular reaction.